Alright, welcome back to Rock the JVM. I'm Daniel, and in this video I'm going to talk about functional collections in Scala. Now, this video is more beginner friendly, so all you need is a basic understanding of Scala syntax, functions and partial functions, and obviously collections. And in what follows, I'll share some ideas about functional collections that many existing Scala developers are quite unaware of. And these ideas are actually what sparked my interest in Scala and functional programming in the first place some 10 years ago when one of my friends was bragging about how his mind was being blown away by some of the ideas that I'm going to show you in this video. So this is a compact version of a thought experiment we follow and then write code for in the advanced Scala course, which I'm also going to link in the description to this video. And otherwise, no libraries are required for this video as we will write plain Scala. As always, I'll write code from scratch, so if you want to follow along, open your code editor and write code with me, and whenever you need to get back to these concepts, refer back to this video or to the written form at the blog with the link in the description as always. So here we are in our beloved code editor. So I've created a small object called functional collections. I'm going to create a main method just in case we need to test anything. And I'm going to start describing functional sets. And think of sets for a moment. These well-known collections of objects that don't allow for duplicates. Now, the implementation of sets, be it tree sets, hash sets, bit sets, whatever, doesn't actually matter. That is less important than what sets actually mean. So I'm going to describe a small set, and I'm going to use the set constructor with 1, 2, 3, 4, 5, obviously. So I have a set with 5 integers, and the critical API of a set consists of 3 fundamental operations. The ability to tell whether an item exists in the set or not, and that is called contains. The ability to add an element to the set, and in case of Scala, that is the operator plus. And the ability to remove an element from the set. And if it doesn't exist, don't remove it again, of course. So remove. And in Scala, that is the operator minus. So if I want to test whether a set contains the item, let's say 2, I can say a set dot contains 2. Or I can say a set dot apply with the element 2, or obviously because apply is special in Scala, I can say a set invoked with the argument 2. And adding and removing elements are as simple as a set plus 6, and this is a new set. And a smaller set is a set minus 3, for example. And adding 6 returns a new set where 6 is also included, and minus is self-explanatory as always. Now, let's concentrate on this capability for the moment. So, contains or apply. The way we tell whether an element is in the set is by calling contains or apply. Now, notice that the apply method makes this set callable like a function. Now, at the same time, that invocation always returns a value, true or false. So I can say a set applied to value whatever, and this is a regular value, and this is false. And in the first case, it's true, of course. And so notice that a set behaves like a function a to boolean because you can pass any argument of type int, in this case, to this so-called function, and you'll get always a boolean, whether or not the argument is in the set. Now, I would like to propose an absolutely outrageous idea. So I say here that sets behave like functions, but I would like to propose the idea that sets are functions. And I'm pretty sure that exactly 0.02% of you have had the curiosity of diving into the standard collection library to see the intricacies in there. So I'm going to do you a favor and prove that sets are actual functions. So I'm going to go to the set trait, which is immutable set, and then I will navigate to iterable factory of another kind of set, which is the general set trait. And this trait extends iterable with collection.set. I'm going to command click here, and set, the base trait for all set collections from Scala collection, extends iterable with setops, and I'm going to command click on setops, and setops extends iterable ops with, and this is our jackpot, a arrow boolean. So in very, very indirect ways, a set extends this trait, a to boolean. So sets are actual functions. So indirection aside, let's abstract away from this concept a little bit. So a set is a function a to boolean, and that function returns true for all the elements that are in the set and false for all the elements that are not in the set. Now here's a small experiment. So I'm going to go back to my so we have here functional collections. We have quite a few indirections here. So here's a thought experiment. Let's write a small implementation of a set that implements the pure functional interface a boolean. So I'm going to define a trait. I'm going to call this our set. And that is our because it is our set, our own set, that is. And I'm going to type it with the type argument a, and this extends a to boolean. Now, our set extends a to boolean, so obviously we'll have an apply method, but I'm going to define the main contract of a set in terms of the three methods that we described earlier. So I'm going to have a method called contains, and this will receive an argument of type a, and this will return a boolean, obviously. And this will be our main API, and then I'm going to add a plus, which gets a new element of type a and will return a new our set of a. And then I'm going to define another method called minus. So this will remove an element of type a out of the set and will return another set. Amazing. So now because we have our set extends a to boolean, we can now implement the apply method in terms of this contains main API. So I'm going to create apply. And this receives an argument. I'm going to call this x still, and I'm going to implement that in terms of contains. So apply x is actually contains x, and these are the abstract methods that we need to implement. Now, let's continue with an implementation of an empty set, which is correctly typed. Now, the standard library uses a simple object typed with any, and then is being type checked via instance of casting. But I'm going to use some small case classes for our thought experiment here. So I'm going to define a case class. I'm going to call this rEmpty, and this takes a type argument a, no arguments, and then extends our set a, and I'm going to implement the API. So I'm going to copy all of these, and I'm going to paste them here. Contains x returns false for all x's in a, so an empty set of type a returns false for everything, plus returns, and I'm going to question mark here because we're going to see shortly how we're going to do that. And removing an element from the empty set will return the empty set. So I'm just going to return this. All right, so I hope this makes sense. We have a small to-do here. I'm going to mark it here as such. And I want to consider a set given by a property. That is similarly how we were taught in math classes in school. So, for example, if you wanted to consider the set of all natural numbers is something like with braces here, like x in n, the set of natural numbers, where, and this is the bar, and you'll pass a property. For example, if you wanted to describe all the even numbers, so all evens, would be something like x in n, for which x mod 2 is equal to 0. All right, so this is pseudo-mathematically Scala something, all right? So you get the idea. Pure sets in mathematics are described by their properties. Now, some sets may be finite or infinite, some may be even countable or not countable. We're not concerned about that. We're concerned about the fact that sets are described in terms of their properties. If you want to dive a little bit deeper into the rabbit hole, that's the job for the students of the advanced Scala course if you want to check that out. But let's try our hand at declaring a small set in terms of the property of their elements. That is a property-based set. So I'm going to define a small class, case class actually. And I'm going to define a case class. I'm going to call this pbSet for property-based set. I'm going to type it with a, and I'm going to give it a constructor argument in terms of a property. So property as a to boolean. All right, and this extends our set a. Now, what is the contains method going to do? Well, contains method is going to return true if the property will hold for that particular element. So if I want to define contains, then I would define that in terms of property. So I'm going to say property applied to x. Now, what do we do if we wanted to add an element to the set? So I'm going to add the element plus, the method plus with an argument of type A, and this will return an R set A. Now, how do we add an element to a set that doesn't really have an array or anything to store elements in? Well, we are defining a set in terms of its property. So we have a bunch of elements described by the same property, and we want to add another element to it. Well, obviously we will need to define another PB set, so I'm going to have a new PB set with A. Now, what is the property going to be? IntelliJ, I know you're not going to have the answer for me, so get lost. All right, so we have a new PB set of A with a new property that for a given element, the predicate or the property is going to return true if property applies for E, that is for all the elements that are already in this set, or this element E is equal to X. So I'm going to have E equals X. And this is a new property. So for all the elements E, the property returns true if the old property for the original set holds true, or if E is equal to X. So X is theoretically considered in the set. All right. So that's how we define a new property-based set without actually storing X anywhere. So I'm going to define a method called minus with another element of type A, and this is going to return in our set A. And this, I'm going to implement that with an if clause. So I'm going to say if contains X, then I'm going to return a new property-based set of A, where for every element E, the property will return true if we have property applied to E, and E must not be equal to X. So I'm going to say E not equal X. So X will definitely not be in this new set because this new predicate will not hold for it. Otherwise, I'm going to return this same set because in this case, X was not in the set to begin with, so I'm going to return the same set. So I'll give you a couple of seconds or even a minute or two to digest what we've just written here. So let's look at the main API method. So the set is all about the property of the element, so contains returns true only if that property is satisfied. Then adding an element means adjusting the property so that it also holds true for the element that we want to add. And removing the element means adjusting the property so that it definitely returns false for the element that we want to remove. And that's it. The set will not contain any duplicates nor change if we try removing a non-existing element, because neither of these operations make any sense now. So coming back to the to-do that we had here, the way that we're going to implement that is a new property-based set of type A, where the property will hold true only if the element E is equal to this particular element that we want to add as argument. So E is equal to X. And this, by the way, is a single element set, and this is also a property-based set where the property only returns true for that particular element. And of course we can test this out. So let's make a small helper method that will allow us to build sets a little bit more easily. So I'm going to define a companion object for our set, and I'm going to define a small apply method, provided I can actually type correctly. And I'm going to get a type argument A, and I'm going to pass in some values as a var arg. So I'm going to say A star, and A star is actually a sequence that we have access to. So we have values, and I'm going to use fold left, and I'm going to type that with rset A. This is the type that we're going to return at the end, and I'm going to start with a new rempty with type A, and the combination function is going to be set plus incoming element. So I hope that makes sense. You've done collection folding before, I assume. And with this helper method in place, we can go to main and we can define our first set. So I'm going to use first 5 elements as an rset of int. And I'm going to use rempty +1 +2 +3 and then +4 +5, and then I'm going to test it out. So I'm going to have a print line. I'm going to say first 5 elements contains 2, or simply invoked with 2 because it's a function, damn it. And then I'm going to have first 5 elements invoked with the number 56, and the first thing will return true, and the second thing will return false. And if I go ahead and run this application, should only take a few seconds, and then we get our expected results. So we have true and false. Let me go fancy now. I'm going to use rset, and I'm going to invoke the apply method with a var arg 1 2 3 4 5, and then I'm going to run, and I'm going to expect the exact same thing. So we have true and false. Amazing. Now, I'm also going to show you a trick that I think I discussed in one of the videos here on the channel in the uses for underscores in Scala, and this is a lesser known feature of underscores, that you can pass a collection as a var arg expansion. So you can say 1 to 1000, and if you pass it like that, then 1 to 1000 is going to be considered as an object with rset. So rset passed with an object, so it will be an rset of ranges, not an rset of int. But if you want to pass all the 1000 numbers here, as I hope you would expect here, then you would put colon and then underscore star. So you will expand this collection to be a var arg that you pass to the apply method of rset. Ain't that cool? So this will be 1000 numbers, and I'm going to adjust this as such. So I'm going to rename this, and I'm going to have first 1000 elements. And now I'm going to run this. And now I'm going to get true and true because 56 is too small a number. And now if I run with a bigger thing, I'm going to return false. Of course. All right, so is this cool or what? Now, the interesting thing about this set definition is that you can now declare infinite sets just based on their property, because if you remember this mathematical definition, I have not forgotten about it. So I'm going to go to main, and I'm going to define val all evens, and I'm going to define a new PB set of type int, and I'm going to say underscore mod 2 must be equal to 0. And this will be an rset of int. So notice that we can now define a whole bunch of elements in one singular declaration with just their properties. And now I can obviously test that out. So I'm going to print line, say all evens contains the number 56. And this should be true. Last time I checked. And if I do all evens with 5, 6, 7, which is not even, and I'm going to return false here. And let me go ahead and run this application, and let me see my final results. So we have true, false, true, false. All right, so notice that we can simulate the mathematical definition of a set by describing a set as a function. And with this definition of a property-based set, you can add a bunch of other operations on sets, including intersections, unions, differences, concatenations, even with infinite sets. So I would really encourage you to go wild and pause the video, try to experiment with this kind of definition. Now, the idea that a set could be a function without actually storing all the elements blew my mind when I first discovered it roughly 10 years ago, because I was always under the impression that a collection should always hold all the elements that it contains. But here we are with a completely different approach to it. Now, of course, nobody's naive. Memory is not free, so we're storing increasingly complex properties instead of storing actual elements, and these properties are in increasing complexity and with increasing memory usage. So you don't get memory for free, but the mental model is the best value for this idea. So if you get the idea of a set as a function out of this video, then I've done my job well. Now, with this kind of idea clarified, we can easily extend it to other collections. For example, you can think of a sequence, and I'm going to define a sequence, and I'm going to use the seek apply method. So I'm going to say seek with 1, 2, 3, and the actual implementation of this sequence might be anything else, maybe a vector or a list or whatever, but the main API of a sequence is that it can give you an element at an index. So if you say a seek applied to the element 1, to the index 1 that is, then you'll get the second element out of the set, so this will be true 2, and if you get a seek with the argument 5, then this will throw because the index 5 is out of bounds. So, question for you. What functional thing is invocable like a function but is not actually applicable on all possible arguments? Now, as a hint, it starts with P and rhymes with partial function. And yeah, I said it. Sequences are actual partial functions. And the argument of this partial function is int, because this is the index at which you want to access an element, and the return type is the type of the element that the sequence actually contains. So this will be a partial function from int to the type A that the sequence contains. And this is also found in the standard library if you dig hard enough. So I'm going to go to seek, and we have immutable sequence, and we have extend seek factory delegate whatever, and this extends iterable with collection seek, and this thing contains iterable and with partial function from int to A. So this is your jackpot over here. The sequence extends partial function from int to A. So you got it from the standard library. A sequence is a partial function. Now let me go back to my code. So as a mental exercise, I would invite you to try implementing a sequence as a partial function from int to A and see where you get. Now the same idea applies to maps too, because maps are invocable objects on a key, returning a value if it exists or throwing an exception if it doesn't. So for example, if I define a map as a map of, for example, string and int, I'm going to define map with a bunch of tuples, and I'm going to use Daniel with 1, 2, 3, and let's say Jane with 4, 5, 6. Now this map is invocable like a function because I can say a map with the argument Daniel, and this will give me back the number 1, 2, 3. And if I get a map with Jack, then this will throw, because Jack is not a key in the map. Same thing. What functional thing, or one functional concept you know that is invocable like a function, but not on all possible arguments, where it throws in case something happens? And the same thing applies. A map is also a partial function. So maps are partial functions from keys to values. Now, if you want me to prove this for you, I can go to immutable map, and then we have iterable with collection.map. I can go here, and then we have iterable map ops. I can go to map ops here, and this extends iterable ops with a bunch of blah, 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 and then partial function with k and v. So if you dig hard enough, a map extends a partial function from keys to values. All right. So we've just learned that a whole swath of critical Scala collections are not just functional, quote unquote, but they're actual functions that you can invoke. So if your mind was at least moved a bit, not necessarily blown away, I'm really happy for this video, because these kinds of concepts make functional programming great and Scala awesome. So if you like this video, go ahead and click the like button for me and subscribe to the channel for more videos like this. Hit me in the comments. I read every single one. Check me out on Twitter and LinkedIn. I post fresh updates, including on upcoming materials, and check out the blog and the Rock the JVM website. I have tons of content and courses on Scala and functional programming, and Awk and Apache Spark and cats and all sorts of goodies. Until next time, I'm Daniel, signing off.